3. The cord connected one end of a block, slide on an inclined plane, the other end wrapped around the cylinder, resting on pressure at the top of the plane is shown. Determine the speed of the block after it's traveled 1 meter along the plane, starting from rest of the following circumstances. So your best approach here on this is the idea of conservation of energy, mechanical energy, in the first case. Because with no friction, and I'm assuming no resistive torque on the cylinder, we have no non-conservative forces. So all of our energy stays as mechanical energy. So we can look at the amount of gravitational potential energy it has at the beginning, and that will be equal to the amount of the change in that gravitational potential energy will be equal to the amount of kinetic energy both the block and the cylinder and actually the rope gain after this movement of 1 meter. The cord we're assuming is light, so we don't have to worry about it. And also that the cord is in a single layer on the cylinder, so we don't have to worry about that, the radius changing either. And we have our cylinder is, I'm assuming, a solid cylinder, since they don't tell us it's hollow. So where I'm starting here for number 3 is for A, the conservation of energy. And of course, mechanical energy is the one I'm really concerned about. So its potential energy, gravitational, of the system is going to equal the kinetic energy of the system. Right? The change in height, if we take kind of a mini triangle here with a hypotenuse of 1 meter, this is 30 degrees. So our change in height is just a sine of 30 degrees. 1 meter times sine of 30 degrees, right? So we've got mgh equals the kinetic energy of the box, which is going to be translational kinetic energy, and the rotational kinetic energy of the cylinder. And that's going to be purely rotational since it's not moving translationally, just like the box will be just translational kinetic energy since it's not moving rotationally.
Wait, I'm sorry. What is there's a kinetic energy of
cylinder?
Oh.
CYL. Okay. It's okay. Not a problem. Questions are not worried. The gravitational potential energy, the one that changes is, of course, of the box, right? Not of the cylinder, because there is no potential energy stored in the cylinder. We would need to either change the height of the cylinder or have a spring or something else to store mechanical potential energy. It doesn't have that. So where we're going here is this will be the mass of the box, gravity, our height, which is our 1 meter, sine 30 degrees. This will be 1/2 m of the box, velocity of the box squared, which is, I believe, what they ask us to find. All right? Yeah. Plus 1/2 I omega squared, Now, a couple other identities that help us at this point is the fact that it tells us that the rope isn't slipping. Well, if we hear that, see that term, or have that situation where we're not slipping, that's when we know that what's valid, so not slipping, means that omega times r equals v. So that's relationship between the translational motion and the rotational motion is only true if there's not slipping going on. If there is slipping, then this relationship is not true. All right. The other identity that we know because of this, since it's a cylinder, its I is going to be 1/2 m r squared. And that r, I'm going to change that to a lowercase r so that it's clear that I have the same r's functioning here. Right, this would be the mass of the cylinder. So let's put a cylinder in there. So really now it's just plug in and solve, because if we put everything in here that we have, mass of the box, change in height of the box, 1/2, mass of the box, which we have, velocity of the box, which we're looking for, plus 1/2 times 1/2 mass of the cylinder, which we have, radius squared, which we have, and we can put in here velocity of the box over radius of the cylinder squared, because that linear motion is the linear motion of the edge of the cylinder, which is the same as the linear motion of the cord, which is the same as the linear motion of the box. So now you can just do the math because you've got everything except VB, right? You want a minute to make sure your numbers work before we move on? Okay. So I'm going to pause the video. All right, so on to part B. Assume the coefficient of friction between all surfaces is mu. First, and they give you a hint. First, determine the normal force on the cylinder and make any reasonable assumptions needed. So we're saying that our cylinder is also has friction on it, not only our box, which when I first looked at it, I'm like, oh, they just mean that now there's friction on the box, and we don't have to worry about the cylinder. But I was glad they gave the hint, because that's good. Now, we could still approach this with energy, but we would need to figure out the amount of non-conservative work done. And we could do that by saying, well, the things doing non-conservative work are the two frictional forces. We could also, though, figure out the things like the acceleration of the whole system and use that and the fact that it moves a meter to do it, which I think probably will be our better approach. So what we're going to need to do is figure out the net force on the box, and with that, the net torque on the cylinder itself. And that's where they're giving you this hint about the normal force, because our frictional force has the same relationship as it does in linear, that the frictional force is created by the two surfaces and the normal force. And that frictional force is now going to create a torque on the cylinder. Say it again. Yes. And the assumption that we're going to make is really that the frictional force is acting at the very bottom of the cylinder. All right, that will be our big assumption there. So there's a single normal force on the cylinder rather than a variety of normal forces along that curve. So we'll try to keep our life a little bit simpler here, but still going to be a fun situation. Let me grab that diagram so that I can do some work with it. Okay, so looking at our system here, we're of course going to have the weight of the box down, a force normal on the box up. If we're looking at the system, of course, I can't label that tension, but we'd have a frictional force on the box up the plane. I'm going to assume that it's sliding down the plane. There's actually an author's note on this problem that when they first put out the problem in the first edition, they made the coefficient of friction too high. And it would end up being that the box went up the hill. And so they have subsequently lowered the coefficient of friction so we can assume the box is sliding down the hill. Here, we're going to have the weight of the cylinder, and we're going to have the force normal of the cylinder also. So we can make some, and then, let's see, I need to do separate diagrams here where we have the weight of the cylinder, the normal force of the cylinder, and we have the tension on it. And that's what I left off, sorry, the frictional force of the cylinder. And then on our box, do the box, force normal of the box, tension, frictional force on the box. And both of these, this one is accelerating this way, and this one I'm going to label its acceleration on a curve that way. It's actually, label that as alpha. And this we could say is A. And since there's no slipping, we again have that relationship that alpha times R equals A because there's no slipping. All right. So if we look at our individual force diagrams here, I could figure out the normal force on the box, figure out the frictional force on it from that, but I couldn't get this tension without knowing the acceleration. With the cylinder here, I could figure out the frictional force. Again, I don't know the tension because I don't know the acceleration on this. So I'm going to end up wanting to get rid of those tensions and just working with the acceleration. So that's how I'm going to kind of bring them together. You can think about it in a system sense. that the tensions are equal to each other, so they disappear, or individually here. So I'm going to first do the rotational motion up top. So I'm going to do my rotational part of this. And in my rotational world, of course, sum of the torques equals I alpha. That same relationship as linear, where we have Newton's second law. So here's Newton's second law for rotational. And the things creating torque on my cylinder here are the tension and the frictional force. I'm gonna say, maybe I should do it as an aside here. Let's do friction over here. We'll look at our two frictional forces and do a couple assumptions here. We're going to say the frictional force of the cylinder is mu weight of the cylinder. And we're going to say that the frictional force on the box is going to be mu, the component of the box's weight, which would be the cosine of theta, or what is it, 30 degrees in this case, right? All right, so those are the two assumptions that we're going to make there. Okay, I'm slightly worried about the normal force on the cylinder, my only concern. Because if I do my vector triangle to do the components of the weight of the box, this angle in here is theta, remember? So it's cosine theta. Let's go ahead with this, but I'm a little worried about our normal force being just the weight of the cylinder. Let's go for it. Okay. So my torques here, I'm gonna get a clockwise torque or a negative torque. We'll call it positive. Torque created by the tension, and then an opposite torque created by the friction. So those are going to oppose each other. So the torque created by the tension would be T and times R, radius of our cylinder. The torque created by the frictional force would be the frictional force of the cylinder times R. That's going to equal my I, which I know is 1/2 mass of the cylinder R squared times alpha. I really can't go any further without knowing the tension here on my rotational end, right? Oh, I can go one more step. I can go 1/2 MC R squared A over R, get it in terms of the linear acceleration. All right. And then, so that's the rotational side. Let's jump over to the linear side of the box. In the linear side, I'm looking parallel to the plane, and down the plane, I'm going to have mvg sine of 30. That's my force down the plane. Up the plane, I'm going to have my tension and my frictional force on the box, and those are going to come together to cause, remember, sorry, sum of the forces equals MA. Mass of the box times A. So nicely, I have both of those in the same sense. I'd like to get rid of tension. So maybe I'll solve this linear one for tension. And am I good? So we're going to have MVG sine 30 degrees minus mu MVG cosine 30 degrees minus MVA equals T. All right, solving that for tension. And then I can substitute that in for my tension up into my rotational work there. And that'll leave me with the only thing I don't know is my A. And I can find my acceleration, and then from that acceleration find, use like, d final squared equals v initial squared plus 2AD to find it. So, yeah, it's just algebra now. Let's try, you try it, I'll try it, let's see if it works. I am still just a little bit worried about that frictional force on C being equal. So, listen to all this stuff, blah, 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 blah. Yeah. This one, I don't know what got recorded and what didn't. It'll make an interesting video, but 6 we talked about. So the 2, let's see, what can we offer on 2? Again, this one I would look at what's its total kinetic energy before hitting the slope. So, it's translational and it's rotational. You know that the identity of omega times r equals v holds because it's not slipping. And then look at how much gravitational potential energy it could gain. And then also, then with V, you could look at that as, well, I would actually look at it as a power question for B. Using that relationship that power is the rate that work is done, and the rate that work being done on this is changing the kinetic energy. The thing doing that work is the component of the weight in the direction. So the vertical part, the weight on it. Interesting. Yeah.